For the second part of Chapter 10, Reconstruction of Past Climates, we'll look at past life, chemical analysis of animals, floral evidence, pollens and tree rings, and then we'll look at climate change over geologic time, looking in the deep past first, and then looking at the Pleistocene periodicity, those timed glaciations in time and Milankovitch cycles, finally looking at the climate since the last ice retreat, and how the correlations between temperature with sunspots and volcanism came about. Past life. Since animals have preferred physical conditions in which they live, we can infer past climate based on their past distributions. One must be cautious when analyzing lake or ocean-dwelling creatures, especially those lower in the water column, since these provide a buffer from the climate at the surface and the environment where these animals live. Ocean sediments contain vast amounts of plankton. Each type of plankton has an optimal temperature zone. They will migrate towards that zone as climate changes. Here's an illustration showing an accumulation of plankton at the surface. Of course, they do need abundant nutrients to be there, but they'll also have optimal temperature zones. As they die, they'll sink to the ocean bed and form sediments, which we can use to infer temperature later. Past life, chemical analysis of animals. Carbon-14 dating. C12 is a lighter isotope of carbon and is stable, whereas C14 is radiocarbon. The proportion of C12 to C14 is relatively fixed in live organisms. This is because there's a source of C14 in the upper atmosphere, where high-energy neurons change N14 to C14 over time. Animals ingest C14 at about the same rate as it decays within them. Once the animal dies, however, the C14 decays at a known rate and is not replenished because the animal is not ingesting. Thus, looking at the ratio of C12 to C14 can give the age. This technique's limited to thousands of years since all C14 will decay by then. Now the point of this is to look at the distribution of animals, which is going to depend on their optimal temperature and moisture conditions, and also be able to date how long that animal has been there, so you can get a time frame for your climate. Also, as we've talked about, we have oxygen isotopes. During cold polar years, which are well correlated with globally cold years, heavier oxygen isotopes are deposited in the ocean. It's due to more condensation en route from the tropics to the poles when you have an extreme temperature gradient. You are what you eat, thus the plankton will have higher amounts of heavy isotopes on colder years. Here again is marine mud oxygen isotopes from plankton, definitely higher delta values during cold periods. There's more heavy isotopes in the ocean as a result of that condensation on cold years. Plants are distributed today based mostly on their temperature and moisture tolerances, and they should have been in the past as well. Of course, we'll look at these classification schemes called the Köppen classification, which uses the distribution of plants to define climates around the globe at the end of the course. Physiology. The plant physiology can be used to infer climate too. For instance, if your plant has a lot of drip leaves, shown here to the lower right, that means there must have been excess water in that type of climate. By having drip tips on the leaves, what the plant's trying to do is find a way to evacuate that water, get it away from its root system because it already has plenty of water. You can also look at the root structure in the water table. If the roots are particularly deep of the plant you dug up, that probably means it was arid and the water table was found far down. In other really wet environments like the jungle, the roots are really spread out along the ground for stability in such a wet and soggy environment. Also, arid environments tend to have plants with thicker leaves to conserve water within them. An example would be the jade plant. Also, the number of stomates in a plant corresponds to the amount of CO2 in the past. Stomates are where gases are exchanged and where evaporation happens within the plant. So therefore, if there's a lot of CO2 around, over time, the evolution of the plant will be to lose stomates because they don't need as much exchange. They don't need to be pulling as much CO2 in because the concentrations are higher. So high concentrations of CO2 typically have plants with less stomates. Pollens are particularly useful because they have very durable outer walls. They withstand long time frames. They're very well distributed. That's the whole point of pollens, for the plants to distribute them widely. Layered sequences are very optimal. Looking here at the right graph, here's layers of pollen. Maybe you have pollens from oak, beech, spruce, which are trees that typically like warm and moist conditions. And then below that in the middle layers, you might have pine and spruce, which definitely like cooler conditions. And then maybe you have a layer of mostly pine, which also prefer cool conditions. So looking at the layers of the pollen, you can get an idea of the plant distributions and also the climate. A tree's annual rings will be thicker during a year that had good growing conditions. That might be just the perfect balance between moisture and temperature for them. You can overlap live and dead trees to get a 10,000 year record or so. So the oldest trees we have are bristlecone pines, and they only go back about 5,000 years. So if you take a live bristlecone core and you're looking back 5,000 years, you could find another petrified bristlecone, and you can overlap the rings, which have obvious consistency between them, to extend the record further back. Here's a tree ring core just to show you that you don't necessarily have to cut the whole tree down to get an idea of the rings. You can take a core and look at it just like an ice core. Climate change over geologic time. So we'll look in the deep past a bit here. For the most part, this class will focus more on what's happening in the last 10,000 and in the modern day to understand how climate change might happen in the future. The first thing to mention, this graph on the right shows the beginning of Earth here at 4.6 billion years ago. Obviously, we don't have a great idea of what was happening climate-wise back then, but the ideas we do have mostly come from rocks. And they've drawn a line here to separate. This is not an average temperature, and they're taking anomalies from that. What it is, it's a line where if you're in the blue here, you have ice caps on your poles. If you're in the gray zone, there are no ice caps at all. So knowing how the graph is made, you can clearly see that Earth is presently colder than in the distant past. It's more common for the Earth to be quite warm with absolutely no polar ice in the distant past. There is perhaps 6 glaciations in the past, some very extensive. There's been a general decline in CO2 concentration over the last 100 million years, from this peak during the Cretaceous down to the Pleistocene extending to now. In the Pleistocene, the last 2 million years, there's been fairly quick transitions from glacial to interglacial periods. So when viewed on these long time scales, we are considered right now to be in a glacial interval because there is polar ice. Within that glacial interval, however, there's oscillations during the Pleistocene going from maximum polar ice to minimum and back. But the whole time's been a glacial interval because there's consistently been some ice at the poles. So the Pleistocene extended from 12,000 years ago to 1.8 million years ago. This ice core covers about 400,000 years, so about a quarter of the Pleistocene. The Holocene period, on the other hand, was from 12,000 years ago to the present, a time of more stability. And also the last glacial maximum was about 20,000 years ago. Recall that these shifts during the Pleistocene were really correlated with Milankovitch forcings, specifically the eccentricity cycle. The Pleistocene record is symptomatic of instability, which requires positive feedbacks. So just like the Me index, which looks at the El Nino, La Nina oscillations, this is also a symptomatic time series of positive feedbacks. It doesn't have one standard where it stays stable at. It's transitioning from one state to another. Why it's so periodic seems to be that the Milankovitch forcings perturb it in one direction, but those forcings are not nearly enough to explain the large temperature deviations. So what kind of positive feedbacks do we have in the system to help explain these amplified transitions? Well, we can look at option A here. When it's colder, there's going to be more snow and ice, more reflectivity, therefore less solar absorbed, and colder. That's called the ice albedo feedback. It's a very strong feedback, especially in the Arctic right now. When it's colder, the oceans become more soluble. To prove that to yourself, open up 2 cans of soda, one warm, one cold. You'll find the one that's warm goes flat quicker than the one that's cold, which means that the warm liquid cannot hold those bubbles or those gases in as well as the cold liquid. Therefore, cold oceans and cold liquids are more soluble. So when it's colder, the oceans take in more CO2, leaving less for the atmosphere, making it colder because you're taking away greenhouse gases. When it's colder, it's typically drier on long time scales because there's less evaporation overall, therefore less vegetation on land supported by less vapor, therefore higher albedo because vegetation has a relatively low albedo. You take it away, it's going to raise the albedo, making the climate system colder. On longer time scales, if it gets colder for a long period of time, you're going to get a lot of ice frozen at the polar caps, taking it out of the seas, lowering the sea levels, making the ratio of land to water go up because now there's a lower sea level exposing more land. That raises the albedo because land has a higher albedo than water, again making it colder. So all of these positive feedbacks are very important in helping amplify these little perturbations that seem to be in tune with our orbital cycles. Looking at the climate since the last great ice retreat 20,000 years ago. This graph is looking back 20,000 years. So pointing out features of this graph, there's the last glacial maximum. It does have orbital explanations with cool summers there. And then you're looking at the Younger Dryas, which was more of a thermal hailing event. Our best science suggests that. And then you're looking at the Holocene climatic optimum, also an orbital feature, featuring very warm northern hemisphere summers, melting that snow, not letting glaciers build up. What kind of orbital forcings would cause the northern hemisphere summers during the climatic optimum to be warmer than our summers today? Now, choice A, higher obliquity than today, that works because that means you're tilted more towards the sun during your summer. The sun's coming in more perpendicular, raising your solar flux. Lower obliquity doesn't work for the opposite reason. Northern hemisphere summer at perihelion would be good because therefore you're just physically closer to the sun, giving you a little more solar flux during that season. So the answer that works is D, both A and C only. Temperatures generally fell from the Holocene climatic optimum to about 3,000 years ago, but then started to rise and got to a new maximum called the medieval warm period. The medieval warm period was roughly from 600 to 1200 AD. This is a time where the Vikings occupied Greenland. And actually grew plants in the southern part of Greenland. However, lowering temps around 1400 AD isolated some of them, and then others migrated away. The climate just got too cold to support them in Greenland anymore. In Europe, the temperatures were warmest at about 1200 AD. We know this because farms were spreading to higher elevations. They were trying to get out of that warm air to a cooler spot to grow the same plants they had originally grown, and in the 1300s, the cooling forced them back down. This cooling period that happened after the medieval warm period is shown here around 1300s as a sharp decrease. What happened was the ice sheets advanced southward from the North Pole. This increased the equator to pole temperature gradient, and therefore the jets sped up significantly. That caused a period of intense storminess and coastal flooding from 1250 to 1350 AD. Estimates are that up to 400,000 people drowned from these storms in the North Sea. And this and the arrival of the bubonic plague in 1346 killed 25% of Europeans, so a large impact from climate change. The North Atlantic climate reached a cooling maximum in the late 1500s that's called the Little Ice Age, shown here. It was not just one single cold period, it was episodic cold spells. Some years would be very cold, some years not so bad, but overall it was a cold time. How we know it happened, there was lowering of tree lines, advancing mountain glaciers, frozen canals, etc. Here's an etching for the Little Ice Age in the French Alps, showing an extensive glacier coming into town, and then a photo from 1966 where that glacier is well receded. And here's a painting from 1565 from the Dutch that shows a winter landscape with skaters along a canal, and those canals are certainly not frozen these days, so unusual cold weather. Volcanoes do emit some CO2, causing warming over long time scales and unabated by weathering processes. That can be important. But in shorter time frames, what's really important is the aerosols that they emit, which tends to cool the globe on average. Volcanism effects during the Little Ice Age and medieval warm period? Yes, it does correlate well. The Greenland ice cores show increased volcanism during the Little Ice Age period and decreased volcanism during the medieval warm period. So it is correlated but not conclusive. Sunspot variability in climate. Extreme sunspot minimum events. There's been some minimums here, the Wolf minimum, the Maunder minimum, the Sporer minimum. Two of those minima do match up well with the Little Ice Age. Extreme sunspot maxima happened in the 12th and 13th centuries, and they do map with the medieval warm period. But not all the past climate changes map well at all with sunspot or volcanic activity. Is it coincidental? Is it important, but there's other important fish in the sea? So again, there is some correlation there, but the recent climate shift seems entirely disconnected to sunspot activity or volcanism. So this is called the hockey stick temperature reconstruction, which uses data from tree rings, corals, ice cores, and historical records to go back to 1000 AD. And this gets some heat in the literature because of their analysis using tree rings. However, it has been justified by many peer-reviewed articles since then. And you can see that the climate hasn't changed much. There's some fluctuations, but then the recent jump since the Industrial Revolution, which we measure directly with thermometers, is quite anomalous. So you can clearly see over that 1,000-year time scale, our recent warming is very anomalous, and this is why it's called the hockey stick. Here's the blade in the last century. So we've seen this graph before, and it simply states that the recent 50-year climate trend seems entirely disconnected to sunspot activity or volcanism. Key points from this lecture: past life. We can infer past climate since plants and animals have climate tolerances. Chemical analysis of plants and animals reveals their age and the past climate as well. Looking at long-term climate change, we found that warm is more normal over periods of billions of years for the Earth. Quick climate shifts in the Pleistocene seem timed with the orbital shifts, but there's certainly feedbacks that must amplify those perturbations. And then the climate since the last glacial retreat, we've had warming associated with orbital cycles. In the last 1,000 years, overall cooler conditions when volcanic, warm with more sunspots. In the last 50 years, however, or even a little bit further, fossil fuel CO2 tends to correlate the best with the temperature increase.